There's something hauntingly beautiful about the unknown, those corners of the universe where science meets mystery, where the rules we think we understand begin to bend. Picture a star, but not the kind you see twinkling in the night sky. This one is invisible, lurking in the shadows of space, so dense and strange it defies everything we know about how stars are born. These are dark stars, objects so mysterious they might not even exist, and yet, if they do, they could shatter our understanding of the cosmos. Imagine a celestial body so powerful, it bends light itself into oblivion, a place where gravity wins and nothing escapes. This isn't science fiction. This is the cutting edge of astrophysics, where the line between theory and reality blurs. For centuries, humanity has looked up at the stars and wondered what else might be hiding in the vast darkness. Now, scientists are asking an even more thrilling question. Could there be stars we can't see at all? Dark stars, if they're real, would be unlike anything we've ever discovered. Instead of burning bright with nuclear fusion like our sun, they might be fueled by something far more exotic: dark matter, the elusive substance that makes up most of the universe's mass. These phantom stars could be lurking in plain sight, invisible to our telescopes, yet shaping the very fabric of space around them. And if we find them, everything we thought we knew about how galaxies form, how stars live and die, might need a rewrite. This is the kind of discovery that changes textbooks. It's the sort of mystery that keeps astronomers awake at night, staring at data, searching for clues in the quiet hum of the cosmos. What if the universe is hiding entire populations of these dark stars, silent giants drifting unseen between the constellations? What if they're the missing piece to puzzles we haven't even solved yet, like the true nature of dark matter itself? Today, we're diving into one of the most fascinating what-ifs in modern science. We'll explore the theories, the evidence, and the mind-bending possibilities of dark stars, objects that could be hiding in the shadows of space, waiting to rewrite the story of our universe. Buckle up, this journey is going to take us to the very edge of what we know and beyond. To understand dark stars, we have to go back, way back, to the very beginning of time itself. Picture the universe in its infancy, a seething, chaotic sea of energy and matter just moments after the Big Bang. In those extreme conditions, something extraordinary might have happened. Scientists speculate that the first stars weren't like the ones we know today. Instead, they could have been something far stranger: primordial dark stars, colossal monsters fueled not by nuclear fusion, but by something far more mysterious: dark matter. Here's the staggering part: these hypothetical dark stars wouldn't just dwarf our sun, they would swallow it whole, millions of times over. Imagine a single star with the mass of an entire galaxy cluster, glowing faintly with the eerie energy of annihilating dark matter particles. Unlike ordinary stars, which shine because of fusion reactions in their cores, dark stars would draw power from the annihilation of dark matter, a process so efficient it could keep these giants burning for millions, maybe even billions of years. But why haven't we found them? The answer lies in their very nature. Dark stars, if they exist, would be incredibly dim. They wouldn't blaze like our sun, but emit a subtle, cold light, easily lost in the vastness of space. And here's the real challenge: our telescopes are built to detect the familiar signatures of ordinary stars: heat, light, radiation. But dark stars would barely register, hiding in plain sight, cloaked by their own strangeness. That doesn't mean astronomers aren't looking. Cutting-edge observatories are now searching for faint, anomalous glows in the distant universe, signs that these dark leviathans might still linger in the cosmic shadows. If we find even one, it could be the missing link in our understanding of dark matter and rewrite the story of how the first stars were born. Until then, these dark giants remain one of the most tantalizing what-ifs in astrophysics, a ghostly echo from the dawn of time. The idea that dark stars might still exist today sounds like something straight out of a cosmic ghost story. but the universe has a way of keeping its oldest secrets hidden in plain sight. If these primordial monsters formed in the early universe, could they have survived 13.8 billion years of cosmic evolution? The answer might lie in the quiet, shadowy outskirts of galaxies, places where dark matter gathers in thick, unseen halos. Think of a galaxy like our Milky Way, not just as a glittering spiral of stars, but as a vast island wrapped in an invisible cloak of dark matter. Within these halos, the conditions could be just right for ancient dark stars to endure. Simulations suggest that if a dark star formed in a region with an unusually high concentration of dark matter, it might not just survive, it could thrive, feeding on an endless supply of dark matter particles colliding and annihilating in its core. But here's the twist: over time, as the universe expanded and dark matter spread thinner, most dark stars would have faded away, starved of their fuel. Yet, in the densest pockets of galactic halos, a few might still linger like cosmic relics, glowing faintly with the last whispers of dark matter annihilation. Astronomers have even modeled how these survivors would look: cold, dim, and eerily stable compared to the short, fiery lives of normal stars. The hunt for these leftover dark stars is already underway. Telescopes scanning the faint infrared glow of distant galaxies might catch a glimpse of something unusual, a light source too dim to be a normal star, too persistent to be a transient phenomenon. Some researchers speculate that certain unexplained signals from deep space, like odd microwave emissions or anomalous gravitational lensing, could be the fingerprints of these ancient giants. If we ever confirm their existence, it wouldn't just be a discovery, it would be a time machine. Dark stars today would be living fossils, untouched since the universe's infancy, holding clues about the wild, uncharted era before the first ordinary stars ignited. They could reveal secrets about dark matter's behavior, the formation of the first galaxies, and even the fate of the cosmos itself. Until then, they remain one of astrophysics' greatest hypothetical treasures, hidden in the dark, waiting to be found. Now, let's shift our gaze from primordial dark stars to something even more bizarre, a cosmic phenomenon so violent it could forge a new kind of dark star in the wreckage of a collapsed neutron star. Imagine the aftermath of a supernova, where the remnants are already unimaginably dense, a city-sized neutron star packing the mass of our Sun into a sphere no wider than Manhattan. But what if that neutron star collapses even further? What if the crushing gravity becomes so intense it smashes the very building blocks of matter into something stranger? This is where quark-novae dark stars enter the picture. In the final moments of a neutron star's life, the pressure might become so extreme that protons and neutrons, particles that normally refuse to break apart, shatter into their most fundamental components, quarks. The result, a quark star, a hypothetical object even denser than a neutron star, a place where matter exists in a state so alien, it defies everything we know about physics. But here's where things get even wilder. Some theorists suggest these quark stars could be cloaked in dark matter, their intense gravitational fields trapping the mysterious particles in a thick, invisible shroud. Unlike ordinary stars, quark-novae dark stars wouldn't shine brightly. Instead, they'd radiate faint, eerie signals, thermal whispers from a surface hotter than the Sun, yet nearly invisible to our telescopes. But they wouldn't hide completely. Their presence might be betrayed by ripples in space-time itself, gravitational waves. When a neutron star collapses into a quark star, the process would unleash a cataclysmic burst of these ripples, a signature that next-generation observatories like LIGO or the future Einstein telescope could detect. And there's another clue: bursts of strange, high-energy radiation. Some astronomers speculate that quark-nova explosions could produce fleeting but intense flashes of gamma rays or radio waves, unlike anything seen in typical supernova. If we spotted such an event, a sudden, inexplicable blast followed by the birth of an object too faint to see, it might be the smoking gun for a quark-nova dark star. What makes this idea so electrifying is that it ties two of the universe's greatest mysteries together: dark matter and the extreme states of matter in dead stars. If quark-novae dark stars exist, they could be cosmic laboratories revealing secrets about how matter behaves under conditions so extreme we can't recreate them on Earth. They might even help us finally understand the true nature of dark matter. Does it interact with quarks? Could it stabilize these bizarre stars, keeping them from collapsing further into black holes? For now, quark-novae dark stars remain a tantalizing possibility, a ghostly counterpart to their primordial cousins. But with every new gravitational wave detection, every unexplained burst of radiation, we edge closer to uncovering whether these shadowy giants are real or just another beautiful what if in the endless mystery of the cosmos. What if some of the black holes we've discovered aren't black holes at all? Imagine an object so dense, so gravitationally dominant, that it bends light and warps space-time just like a black hole, but with one crucial difference. There's no point of no return, no event horizon where matter vanishes forever. These could be electromagnetically silent dark stars, cosmic imposters lurking in the shadows, tricking even our most advanced telescopes. Take the famous first image of a black hole's shadow. That fiery ring surrounding darkness captured by the Event Horizon Telescope. While it fits predictions for a supermassive black hole, some astronomers have quietly questioned whether the data could hint at something stranger. The ring's brightness, its asymmetry, even the way light flickers around it, these anomalies raise a tantalizing possibility. Could we be looking at a dark star instead? Unlike black holes, dark stars wouldn't have an event horizon. Matter wouldn't disappear forever but could pile up in a crushing, dense shell just outside the core. This means light could still escape, though barely, stretched and twisted by gravity into eerie, distorted signatures. From a distance, the effect might look almost identical to a black hole's shadow. But zoom in and subtle differences emerge. A dark star's gravitational lensing could produce slightly brighter edges or flickers of unexpected radiation as trapped particles struggle to break free. It's the cosmic equivalent of spotting a doppelganger nearly perfect, but with tiny, haunting inconsistencies. The implications are staggering. If even a handful of supposed black holes turned out to be dark stars, it would force us to rethink how gravity behaves in the most extreme environments. It might also solve lingering mysteries, like why some supermassive objects seem to lack the violent jets seen in confirmed black holes. Dark stars could be the quiet cousins, bending space without the cosmic fireworks. Right now, the hunt for these imposters is just beginning. New telescopes, like the upcoming Nancy Grace Roman Space Telescope, could spot the telltale flickers of light betraying a dark star's presence. Others might listen for gravitational waves, searching for ripples that don't quite match black hole collisions. The universe loves a good deception, but if dark stars are out there, we're getting closer to uncovering their disguise. Deep in the heart of our Milky Way, something strange is brewing. A pair of colossal gamma-ray bubbles stretching 25,000 light-years above and below the galactic plane. Astronomers call them the Fermi Bubbles, and since their discovery in 2010, they've been one of the most baffling mysteries in our cosmic backyard. These towering structures glow with high-energy radiation, a silent scream of particle interactions we don't fully understand. Conventional explanations point to the supermassive black hole at our galaxy's core, suggesting past eruptions might have inflated these bubbles with searing jets of matter. But there's a problem: the energy patterns don't quite fit. The gamma-ray excess is too smooth, too uniform, unlike the chaotic fingerprints of black hole outbursts. So what if we're missing something far more exotic? What if dark stars are lurking in this story? Picture this: the Fermi Bubbles aren't just remnants of a black hole's tantrum, but the faint, smoldering aftermath of dark matter annihilation. If dark stars or their remnants existed near the galactic center, their dark matter fuel could have ignited a slow, steady burn, releasing energy over millions of years. Unlike the violent bursts from black holes, dark matter annihilation would produce a more diffuse, lingering glow, exactly matching the strange uniformity of the Fermi Bubbles gamma rays. It's a radical idea, but it solves two puzzles at once: the unexplained energy signature and the eerie symmetry of the bubbles themselves. Here's why this theory turns heads. Dark matter is thought to cluster most densely in galactic cores, meaning the Milky Way's center could have once hosted an entire population of dark stars. As these stars aged, their dark matter fuel might have dwindled, causing them to collapse or fade, but not without a trace. The annihilation of leftover dark matter particles drifting in the wreckage of dead dark stars could still be happening today, pumping energy into the surrounding gas and lighting up those colossal bubbles. Critics argue we need more evidence, and they're right, but the pieces fit together in a way that's hard to ignore. The Fermi Bubbles gamma rays align eerily well with predicted signals from dark matter interactions. And if future telescopes detect similar structures in other galaxies, especially those without active black holes, the case for dark star involvement grows even stronger. The implications are staggering. If dark matter annihilation is truly powering the Fermi bubbles, it's not just a clue about dark stars, it's a roadmap. These bubbles could be the first visible signpost pointing us toward the invisible architecture of the universe, a hidden layer of reality woven into the fabric of space itself. Until we know for sure, the Fermi bubbles remain a cosmic riddle, whispering secrets about the dark side of the cosmos. Imagine a dark star not bound to any galaxy, a cosmic nomad drifting through the endless void between islands of light. These rogue dark stars would be the ultimate loners of the universe, untethered from the dense clusters of matter that birthed them, wandering through intergalactic space like ghostly ships adrift in an infinite ocean. How could such a thing exist? The answer lies in the violent, chaotic dances of galaxies themselves. When two galaxies collide, their stars don't typically crash into one another. Space is too vast for that. Instead, their gravitational forces twist and warp, flinging some stars outward like stones from a slingshot. Now, picture this same scenario but with dark stars. If these invisible giants formed in the crowded heart of a young galaxy, a close encounter or merger could hurl them into the abyss. Once ejected, their journey would be solitary and silent. Unlike normal rogue stars, which might still glow faintly as they drift, dark stars would be nearly undetectable. No bright tail, no fiery wake, just an invisible mass carving through the darkness. Detecting these loners would be like searching for a whisper in a hurricane. Without the background light of a galaxy to contrast against, their subtle gravitational influence would be the only clue. Even then, their signals would be drowned out by the noise of cosmic structures. But there's a sliver of hope. Some astronomers propose that if a rogue dark star passed between us and a distant galaxy, its gravity could bend the light from behind it, creating a brief, telltale flicker, a phenomenon known as microlensing. Telescopes monitoring millions of galaxies for such flickers might one day catch one of these dark wanderers in the act. What makes the idea so compelling is that rogue dark stars could solve another cosmic mystery: the missing mass in intergalactic space. We know there's more gravity out there than visible matter can explain, and while diffused dark matter is the leading theory, what if some of that hidden mass is locked inside these drifting dark stars? They might be the invisible glue holding together the large-scale structure of the universe, shaping the voids between galaxies in ways we're only beginning to guess. Until we spot one, rogue dark stars remain a haunting possibility, silent travelers in the deepest dark, remnants of an era when galaxies were young and chaos ruled. Their existence would rewrite not just the story of dark matter, but the history of how galaxies grow, collide, and fling their secrets into the void. And if we ever find them, they could be the key to unlocking the darkest corners of the cosmos. Among the most intriguing possibilities in the hunt for dark stars is the idea that they might not always lurk alone. What if they orbit other objects, locked in a cosmic dance that leaves subtle fingerprints across space? Binary systems are common in the universe, from pairs of stars whirling around one another to black holes spiraling toward collision, but a dark star paired with a visible companion. That would be a ghost waltzing with fire, an elusive shadow tethered to something we can actually see. The key to spotting these hidden duos lies in their gravitational pull. Picture a normal star behaving strangely, wobbling unpredictably, or brightening and dimming in ways that defy explanation. These anomalies could be the tug of an invisible partner. Just as astronomers once inferred the existence of black holes by watching stars orbit unseen masses, a dark star binary might betray itself through the same gravitational whispers. Even without emitting light, its presence would warp the motion of its visible twin, creating ripples in space-time detectable by sensitive instruments. But there's another, more dramatic way a dark star binary could reveal itself: through accretion. If a dark star and a normal star orbit close enough, the dark star's gravity could siphon gas from its companion. Unlike the violent feasting of a black hole, which tears matter apart in a blazing disk, a dark star's meal would be eerily quiet: no fiery X-rays, no brilliant jets. Instead, the stolen gas might simply vanish, piling onto the dark star's surface in a way that emits only the faintest infrared glow. Telescopes scanning for these cold, mysterious signatures could stumble upon a dark star hiding in plain sight. The most tantalizing scenario: a binary system where both objects are dark stars, circling one another in perfect invisibility. Without light or obvious accretion, how would we ever detect them? The answer might lie in gravitational waves. As two dark stars spiral closer over millennia, their movement would send ripples through the fabric of space itself. Subtle tremors that observatories like LIGO could pick up. The pattern of those waves would be unlike anything produced by neutron stars or black holes, offering a potential smoking gun for these shadowy pairs. The implications stretch beyond mere detection. Studying dark star binaries could unlock secrets about how dark matter behaves in dense environments. Does it clump differently around these hidden giants? Could their gravitational interactions reveal new properties of the invisible particles fueling them? Each wobble, each ripple, each flicker of stolen starlight could be a piece of the puzzle, one that might finally bring these cosmic phantoms into the light. Among the strangest possibilities in the dark star mystery is a theory that turns our search for these hidden giants on its head. What if they're not entirely dark after all? Enter axion-photon conversion: dark stars, hypothetical objects that might emit faint, ghostly light under the right conditions. This idea springs from one of the most compelling candidates for dark matter: axions. These ultra-light, wispy particles, if they exist, could solve multiple cosmic puzzles at once, from the nature of dark matter to the baffling symmetry of the universe's fundamental forces. And if axions make up dark stars, their eerie glow might finally give us a way to spot them. Axions are thought to be incredibly shy particles, barely interacting with ordinary matter. But place them in a strong magnetic field, and something extraordinary could happen. According to theory, axions might transform into photons, particles of light, in a process called the Primarkov effect. Now picture a dark star with a searing hot core wrapped in a powerful magnetic field. Axions streaming from its dark matter halo could convert into faint photons at its surface, creating a whisper-thin veil of light around an otherwise invisible object. It wouldn't be the blazing radiance of a normal star, but a cold, spectral shimmer like moonlight glancing off a frost-covered window. This is where cutting-edge experiments come in. Projects like the Axion Dark Matter Experiment (ADMX) are already hunting for axions in laboratories deep underground, using superconducting magnets to coax these elusive particles into revealing themselves. While they're designed to detect actions flowing through space, the same principles could apply to dark stars. If a dark star's action wind converts into photons, next-generation telescopes tuned to specific frequencies might catch its otherworldly glow. The real game-changer could be the upcoming Nancy Grace Roman Space Telescope and the Square-Kilometer Array. With unprecedented sensitivity to faint, diffuse light, they might spot the telltale flicker of action conversion around invisible masses in distant galaxies. Even more tantalizing, some researchers suggest certain unexplained, anomalous microwave emissions from space could already be the faint echoes of action-powered dark stars. What makes this idea so revolutionary is that it flips the script. Instead of searching for dark stars through their gravitational shadows, we might actually see them not as voids but as ghostly halos of converted light. If confirmed, it would be a double discovery, proof of action dark matter and the first direct evidence of dark stars all in one. Until then, these phantom beacons remain one of the most elegant solutions to the dark matter puzzle, a way for the invisible to finally step into the light. At the very edge of our cosmic imagination lies a theory so radical, it ties the birth of the universe to the dark stars hiding in its shadows, Planck stars. These aren't just hypothetical objects, they're relics from the first chaotic moments after the Big Bang, when space-time itself was a seething quantum foam. Picture the universe as a newborn, still hot and dense, its energy so concentrated that gravity and quantum mechanics waged a violent tug-of-war. In that frenzy, tiny knots of space-time might have collapsed into ultra-dense objects, Planck stars, packing the mass of a mountain into a space smaller than an atom. Unlike black holes which crush matter into singularities, Planck stars would hit a limit, rebounding like a cosmic spring before collapsing entirely. Now fast forward 13.8 billion years. What if some of those primordial Planck stars didn't vanish? What if they survived, cooling and darkening into invisible cinders drifting through the modern universe? These wouldn't be dark stars in the traditional sense, no dark matter fuel, no eerie glow. Instead, they'd be fossils of the Big Bang's quantum chaos, their cores still vibrating with echoes of creation. And here's where things get mind-bending. If Planck star remnants exist, they might leave fingerprints in the oldest light we can see, the cosmic microwave background, or CMB. The CMB is like a snapshot of the universe's infancy, a faint afterglow from when space first became transparent. But it's not perfectly smooth. Tiny fluctuations in its temperature hint at the seeds of galaxies, the wrinkles of early gravity. Some theorists suggest that Planck stars could have left their own marks, subtle ripples or echoes in the CMB's pattern. How, if a Planck star's rebound sent shockwaves through the young universe, those waves might have imprinted themselves as anomalies in the microwave background, like footprints in cosmic sand. Hunting for these echoes isn't just a shot in the dark. Advanced algorithms are now scouring CMB data for irregularities that don't fit standard models. Some researchers claim they've already spotted odd, ring-like patterns in the data features that could controversially align with Planck star collisions. Skeptics argue these could be statistical noise, but if the signals hold up, they'd be our first glimpse of quantum gravity in action, a bridge between Einstein's relativity and the fuzzy rules of the quantum world. The stakes couldn't be higher. Confirming Planck star remnants wouldn't just add a new class of dark stars to the cosmic menagerie, it would rewrite our understanding of the Big Bang itself. Were Planck stars the universe's first dark matter? Did they seed the growth of galaxies or even evade detection by hiding inside black holes? Each question unravels another thread in the tapestry of the cosmos, reminding us that the darkest corners of space might still hold the brightest secrets. Fast radio bursts are some of the most baffling signals in the universe, blips of intense radiation lasting mere milliseconds, yet packing more energy than the sun emits in days. Most come from distant galaxies, flashing once and vanishing without explanation, but a handful repeat, flickering on and off in patterns that defy conventional astrophysics. While Magnetar's highly magnetic neutron stars are the leading suspects, some FRBs behave in ways that don't quite fit. What if another invisible player is at work? Enter dark stars not as steady glow, but as cosmic flashbulbs erupting in bursts of dark matter annihilation. Picture a dark star with a turbulent core where dark matter particles collide and annihilate in waves. Normally, this process would be slow and steady, producing faint, continuous radiation. But under extreme conditions, say, if the star's dark matter fuel became suddenly concentrated, these annihilations could spike, unleashing a torrent of energy in seconds. The result, a flare so powerful it could mimic the signature of a fast radio burst. Unlike magnetars, which twist magnetic fields to breaking point, dark star flares would stem from something far more exotic, the violent unraveling of dark matter itself. The most compelling evidence lies in the repeaters. Some FRBs fire off signals at irregular intervals with no clear pattern. Magnetars can explain one-off bursts, but their mechanics struggle to account for the erratic repetitions. Dark stars, on the other hand, might offer a cleaner solution. If their dark matter supply isn't uniform clumping and dispersing due to gravitational tides or collisions with cosmic debris, their eruptions could be similarly unpredictable. One week a flare, the next silence. No magnetic field gymnastics required, just the ebb and flow of invisible fuel. Then there's the frequency problem. Many FRBs skew toward lower frequencies, a trait that fits awkwardly with magnetar models but aligns eerily well with predictions for dark matter interactions. Simulations suggest certain types of dark matter annihilation could produce radio waves in this exact range, as high-energy particles slam into surrounding plasma. It's as if the universe left us a subtle clue hidden in the static. Of course, skepticism is healthy. Magnetars are proven cosmic powerhouses, while dark stars remain hypothetical. But science thrives on anomalies, the data points that refuse to fit. And with each new FRB detection, the catalog of unexplained bursts grows. Could some fraction be dark stars announcing themselves in violent, fleeting whispers? The answer might lie in next-generation radio arrays like the Square Kilometre Array, which could pinpoint FRBs with unprecedented precision. If certain bursts trace back to regions with no visible magnetars, or worse, to patches of empty space where nothing should be erupting at all, the case for dark star involvement suddenly gets much harder to ignore. This isn't just about solving the FRB mystery, it's about rewriting the rules of cosmic energy. If dark stars can flare, they're not just passive shadows, they're active, dynamic monsters, capable of shaping their surroundings in ways we're only beginning to imagine. And if we're right, the next fast radio burst could be more than a curiosity. It might be the first hello from a universe we never knew was there. In 2012, astronomers spotted something strange skimming dangerously close to our galaxy's supermassive black hole, a bizarre object dubbed G2. At first glance, it appeared to be a cloud of hydrogen gas, doomed to be ripped apart by the black hole's monstrous gravity. But as it made its closest approach in 2014, G2 didn't behave like any ordinary gas cloud should. Instead of shredding into tendrils of luminous debris, it held its shape with eerie resilience, slipping past Sagittarius, a star with barely a flicker. This defiance of expectations sparked a tantalizing question: what if G2 wasn't a cloud at all? What if it was something far more exotic, a dark star cloaked in a thin veil of gas? The gas cloud explanation always had holes. For one, G2's orbit was too tight, too precise for something as diffuse as interstellar gas. Gas clouds get stretched and distorted by tidal forces long before reaching a black hole's grasp, yet G2 remained compact, almost like a solid object guiding its own path. Even stranger, its infrared glow didn't match predictions for a pure hydrogen cloud. Instead of the expected thermal radiation, G2's light curves suggested something more complex, perhaps a dense core radiating faintly beneath a gaseous shroud. This is where the dark star theory ignites. Imagine a stellar mass object made mostly of dark matter, its gravity compressing a thin shell of ordinary gas into a shimmering envelope. As it neared the black hole, the outer gas layer would heat up, emitting the infrared glow astronomers observed, while the dark matter core remained untouched by tidal forces. Unlike normal stars, which would be torn apart, a dark star's gravitational anchor, its dark matter halo, could withstand the black hole's pull, explaining G2's uncanny stability. Critics argue we're grasping at shadows. They point to alternative models where G2 is a gas cloud birthed from a colliding star's debris, or a runaway planetesimal wrapped in a dusty cocoon. But these theories struggle to explain the object's persistent structure post-encounter. If G2 were just gas, it should have diffused into a smeared streak across the black hole's accretion disk. Instead, it emerged from its death spiral nearly intact, as if something unseen was holding it together. New observations might settle the debate. Upcoming studies using the James Webb Space Telescope could analyze G2's chemical fingerprints, searching for anomalies that betray a dark matter core. Others propose monitoring its future trajectory. If it loops back around Sagittarius, a star with clockwork precision, that rhythmic dance would hint at a massive, hidden anchor beneath the gas. The implications stretch beyond one odd object. If G2 is a dark star, it suggests these hidden giants might congregate near galactic centers, drawn by the same dense dark matter halos that feed supermassive black holes. Their presence could rewrite how we model the chaotic heart of galaxies, turning passive gas clouds into potential dark matter laboratories. Until then, G2 remains an enigma, a cosmic tightrope walker whose survival defies explanation, whispering secrets about the invisible architecture of the universe. If you're searching for dark stars, don't look up, at least not toward the bright, bustling spirals of the Milky Way or Andromeda. Instead, turn your gaze to the faint, forgotten corners of the cosmos, to the dwarf spheroidal galaxies drifting like ghost ships in the cosmic dark. These tiny, dim collections of stars, some with only a few thousand compared to our galaxy's hundreds of billions, might seem like odd places to hunt for cosmic giants. But their quiet exteriors hide a staggering secret. They're almost entirely made of dark matter. Take the Draco dwarf, for instance. This unassuming satellite galaxy, orbiting the Milky Way at a distance of 260,000 light-years, has a mass-to-light ratio so lopsided, it suggests dark matter outweighs visible matter by nearly 300 to 1. In other words, for every flicker of starlight, there's an invisible mountain of something else, making these galaxies the perfect laboratories for dark star detection. So why haven't we found them yet? The answer lies in the challenges of spotting something designed to stay hidden. Current searches in dwarf galaxies have come up empty, not because dark stars aren't there, but because our methods might be missing the forest for the trees. Traditional surveys look for the infrared glow of dark matter annihilation, the faint heat signature theorized to emanate from these objects. But in dwarf galaxies, where star formation is minimal and interstellar gas is sparse, even that subtle signal could be drowned out by background noise. It's like trying to spot a single candle's glow from across a foggy lake, possible in theory, but nearly impossible with today's instruments. But there's hope on the horizon. New strategies are flipping the script, focusing not on light but on absence. If dark stars exist in dwarf galaxies, their immense gravity should subtly distort the motions of visible stars around them. Imagine a cosmic game of pinball where the paths of stars wobble inexplicably, hinting at an unseen player's hand. Recent studies of the Draco dwarf have already flagged strange stellar velocities that don't fit standard models, anomalies that could, if you squint, align with the gravitational pull of a hidden dark star. The data isn't conclusive yet, but it's a tantalizing thread to pull. The next breakthrough might come from an unexpected tool: gamma-ray telescopes. If dark stars are indeed fueled by dark matter annihilation, the process should produce not just heat, but high-energy gamma rays. dwarf galaxies are famously clean environments with little interstellar gas to muddy the signal, making any gamma-ray excess stand out like a flare in the night. Recent observations from the Fermi Gamma-Ray Space Telescope have detected puzzling gamma-ray emissions from several dwarfs, including Draco. While some argue these could be pulsars or other mundane sources, the emission's smooth, diffuse nature fits eerily well with dark matter annihilation models. The stakes are higher than a single discovery. If dark stars lurk in dwarf galaxies, they could solve one of astrophysics' most persistent riddles: why dark matter halos in these tiny galaxies are so dense and cored compared to theoretical predictions. Dark stars with their unique gravitational footprints might be the missing link, their presence subtly reshaping the distribution of dark matter over billions of years. It's a cosmic feedback loop, dark stars influencing their environment, and that environment in turn preserving them. The hunt is far from over. Upcoming telescopes like the Vera C. Rubin Observatory will map the skies with unprecedented depth, potentially catching the gravitational distortions dark stars leave in their wake. Others, like the Cherenkov Telescope Array, could pinpoint gamma-ray signatures too faint for current instruments. Until then, dwarf galaxies like Draco remain the universe's quietest vaults, places where the darkest secrets might be waiting, not in the void but hidden in plain sight. Every ripple in spacetime tells a story, but some of those stories are whispered in the dark. When black holes or neutron stars collide, they don't just send gravitational waves cascading across the cosmos. They often light up the sky with bursts of X-rays, gamma rays, or visible light. These brilliant flares act like cosmic lighthouses, guiding astronomers to the scene of the crash. But what happens when the collision leaves no trace in the electromagnetic spectrum? What if the only sign is a shudder in the fabric of spacetime itself? These are the dark sirens, gravitational wave events with no visible counterpart. And hidden among them could be the signatures of merging dark stars. Consider the mass gap problem. When LIGO and Virgo detect gravitational waves, they measure the masses of the colliding objects. Most black holes fall into predictable categories: stellar mass black holes from collapsed stars, or supermassive ones lurking in galaxy cores. But a handful of detections defy this logic, revealing objects too heavy to be neutron stars yet too light to fit neatly into known black hole models. These outliers cluster in the so-called mass gap, a theoretical no man's land where conventional astrophysics struggles to explain what's happening. Could these anomalies be dark stars, their unusual masses reflecting the strange physics of dark matter cores? Unlike black holes, which form from the collapse of ordinary matter, dark stars would carry the imprint of their dark matter fuel. Their mergers wouldn't produce the fiery accretion disks or relativistic jets we associate with binary black holes. Instead, the collision might unfold in eerie silence, no flash, no afterglow, just a clean gravitational ripple. Some researchers argue this fits the profile of certain unexplained LIGO events, like GW190521, a merger involving an object squarely in the mass gap. The signal lacked any electromagnetic follow-up, as if the participants were invisible. The key to confirming this theory lies in the details of the waves themselves. Gravitational waves aren't just simple pulses. They carry intricate patterns that reveal the nature of the objects creating them. A dark star merger might produce subtle distortions in the wave, form tiny deviations from Einstein's predictions caused by the way dark matter interacts with spacetime. Next-generation detectors, like the planned Einstein telescope, could spot these anomalies with unprecedented precision, sifting through the cosmic noise for hints of something unseen. There's another clue hiding in the data: spin. When ordinary black holes spiral toward collision, their rotation leaves a distinct fingerprint on the gravitational waves. Dark stars with their exotic interiors might spin differently, perhaps slower or with unexpected wobbles. A handful of LIGO events already show puzzling spin characteristics, hinting at objects that don't behave like standard black holes. If future detections consistently match these quirks, it could be the smoking gun for dark star mergers. The implications are staggering. If even a fraction of mass gap events are dark stars, it would mean these hidden giants aren't just lurking in isolation, they're meeting, merging, and reshaping each other in the darkness. Their collisions could be seeding the universe with strange hybrid remnants, objects neither star nor black hole, but something entirely new. And with each unexplained ripple in space-time, we edge closer to the answer, not with telescopes, but with the silent language of gravity itself. Beyond the familiar forms of dark matter lies a concept so strange. It sounds like science fiction, a cosmic object called a cue ball. Imagine a knot of energy so dense and stable, it could form the beating heart of a dark star, defying the laws that govern ordinary matter. In the wild landscape of theoretical physics, cue balls emerge from supersymmetry, a framework suggesting every known particle has a hidden, heavier twin. Under certain conditions, these hypothetical particles could clump together into sprawling, exotic structures, growing so massive they rival stars in size yet remain nearly invisible. What makes cue balls extraordinary is their resistance to annihilation. Most dark matter candidates, like WIMP, vanish in bursts of energy when they collide. But cue balls are different. Their structure acts like a fortress, locking away energy so efficiently that even the universe's most destructive forces struggle to break them apart. This stability could solve one of the biggest puzzles about dark stars: how they endure for billions of years without dissipating. A cue ball core wouldn't just fuel a dark star, it would anchor it, providing a near-indestructible engine that outlasts galaxies. The connection to Hawking radiation deepens the mystery. Black holes famously evaporate over eons, leaking energy until they vanish, but cue balls flip this script. Their unique properties might allow them to absorb Hawking radiation, effectively using the black hole's own decay as a power source. Picture a dark star perched at the edge of oblivion, feeding on the very forces that should destroy it, a cosmic paradox hiding in plain sight. Supersymmetry paints an even wilder picture. If cue balls exist, they could be relics from the universe's first moments, formed when space-time was a seething foam of quantum fields. Some theories suggest these objects might carry charge from long-dead particles, weaving hidden symmetries into the fabric of reality. Their presence in dark stars would imply something staggering: that the invisible architecture of the cosmos is far more intricate than we dreamed, shaped by rules we're only beginning to glimpse. The hunt for cue ball dark stars is already pushing the limits of detection. Particle colliders like the Large Hadron Collider are searching for traces of supersymmetric particles, while astrophysicists scour the sky for anomalies in gravitational lensing or gamma-ray signals that don't fit known models. A single confirmed sighting wouldn't just prove dark stars exist, it could validate entire branches of theoretical physics, bridging the gap between the quantum world and the cosmic scale. For now, cue ball dark stars remain a breathtaking what if, a reminder that the universe's darkest corners might hide its most brilliant secrets. Whether they're waiting to be found or destined to stay theoretical, one thing is certain: if they're real, they're rewriting the rules of existence itself. Deep beneath the Antarctic ice, where temperatures plunge to unimaginable lows and the weight of the frozen expanse above presses down like a silent ocean, something extraordinary is happening. Particles from the darkest corners of the cosmos are slamming into the Earth, leaving ghostly trails in their wake. The IceCube Neutrino Observatory, a sprawling network of sensors buried in the ice, has spent years catching these cosmic messengers, and what it's found is just as puzzling as it is thrilling. Among the countless neutrinos streaming through space, a handful stand out: high-energy flares with no clear source, clustered in ways that defy expectations. Could these be the faint echoes of dark stars whispering their existence across the universe? Neutrinos are the universe's most elusive particles, nearly massless, indifferent to magnetic fields, and capable of passing through entire planets without a trace. When one finally interacts with the ice in Ice Cube, it creates a faint burst of light, a blip in the data that points back to its origin. Most neutrinos come from predictable sources: the Sun, supernova, or the violent hearts of distant galaxies. But the anomalies, the ones that arrive with staggering energy and no obvious home, hint at something far stranger. Some of these events cluster in patches of the sky, as if something unseen is firing them toward us like cosmic bullets. This is where dark stars enter the picture. Imagine one of these invisible giants lurking in deep space, its core a roiling cauldron of dark matter annihilation. As particles collide and annihilate, they could produce not just gamma rays or gravitational waves, but torrents of high-energy neutrinos flung outward in all directions. Unlike light, which can be absorbed or scattered by interstellar dust, neutrinos travel unimpeded, carrying signals from the darkest, most distant objects straight to detectors like Ice Cube. The most tantalizing clue comes from directional clustering. Some of Ice Cube's unexplained neutrino hotspots align eerily with regions where dark matter is thought to pile up, dense galactic halos or the centers of galaxy clusters. These aren't random scatterings, they're tight groupings, as if something massive and hidden is acting as a neutrino beacon. Of course, skepticism remains. Neutrinos are notoriously hard to trace precisely, and alternative explanations like hidden blazars or rogue neutron stars can't be ruled out yet. But here's what makes the dark star hypothesis so compelling: timing. Some of these high-energy neutrino flares coincide with other anomalies like gravitational wave events or gamma-ray bursts, yet don't match any known astrophysical sources. It's as if the universe is dropping breadcrumbs, urging us to follow the trail to something invisible. Future upgrades to Ice Cube, combined with data from gravitational wave observatories and gamma-ray telescopes, could finally weave these threads together, revealing whether dark stars are the missing link in the neutrino puzzle. If confirmed, the implications would rewrite astrophysics. Dark stars wouldn't just be passive shadows, they'd be active engines churning out particles that pierce the cosmos undetected until they strike a detector buried in the ice. Each neutrino flare could be a fingerprint, a fleeting sign that somewhere in the blackness between galaxies, a dark star is stirring, sending its ghostly signal across the ages. The hunt isn't over. With every unaccounted-for neutrino, the case grows stronger, and the universe's darkest giants inch closer to being unmasked. Some of the most powerful particle accelerators in the universe aren't built by human hands. They're forged in the hearts of dying stars, where magnetic fields twist spacetime into knots and fling matter outward at nearly the speed of light. For decades, scientists have traced ultra-high-energy cosmic rays, those mysterious particles screaming through space with energies 1,000,000 times beyond anything our most powerful colliders can produce, back to violent objects like pulsars and supernova. But there's a problem. Some of these cosmic rays arrive with energies so extreme, their origins defy conventional explanations. Their paths even hint at something unsettling. They're not coming from all directions equally, but cluster in ways that suggest hidden, monstrous engines lurking in the cosmic dark. Could these be the fingerprints of dark stars? Picture a dark star with a magnetosphere gone rogue. Like pulsars, these invisible giants could spin rapidly, wrapping their magnetic fields into coils of unimaginable tension. But here's where the similarities end. Pulsars accelerate particles through a process tied to their visible matter, electrons and protons surfing electromagnetic waves. A dark star's engine would run on something far stranger, the annihilation of dark matter in its core, producing a chaotic soup of exotic particles. As these particles spiral along magnetic field lines, they might gain energy not in steady pulses, but in violent, unpredictable surges, like a storm lashing out with lightning bolts of pure annihilation energy. The result, cosmic rays with energies eclipsing even the most powerful pulsar bursts, their trajectories twisted by dark matter's gravitational pull into strange, anisotropic patterns across the sky. The data already whispers of anomalies. Observatories like the Pierre-Auger array have mapped cosmic ray arrival directions for years, revealing puzzling hotspots, regions where these ultra-high-energy particles seem to originate more frequently than chance allows. Some align with known pulsars, but others point to blank patches of space where no visible object could explain their fury. Even more telling, the particles' energy spectra don't quite match pulsar models. They're too skewed, too extreme, as if something beyond ordinary physics is at work. Dark stars with their dark matter-fueled accelerators could fill this gap, their magnetospheres acting as cosmic pevatrons, particle accelerators, dwarfing even the most powerful terrestrial colliders. But how could we ever prove it? The key might lie in the particles themselves. Cosmic rays from pulsars carry distinct signatures, specific ratios of protons to heavier nuclei, or telltale gaps in their energy distribution. Dark star cosmic rays born from dark matter annihilation could differ radically, perhaps dominated by strange, unstable particles that decay before reaching Earth, leaving behind only subtle traces in detector data. Future observatories, like the proposed giant radio array for neutrino detection, might spot these ghosts by catching the radio waves they emit as they streak through Earth's atmosphere, a faint but distinct scream from the dark. The stakes are cosmic. If dark stars are pevatrons, they're not just hiding in the shadows, they're actively reshaping the universe, seeding galaxies with particles of impossible energy. Their rays could be the invisible force behind mutations in early life's DNA, the trigger for atmospheric reactions that alter planetary climates, or even the source of mysterious, oh my god, particles. Those rare cosmic rays with energies so absurd they seem to break physics. Until we catch one in the act, these dark accelerators remain a tantalizing what if, a reminder that the universe's greatest engines might be the ones we can't even see. There's a region in our own galaxy so shrouded in dust and gas, it's practically a blind spot for astronomers, the zone of avoidance, stretching along the Milky Way's central plane. This swath of sky is so thick with cosmic debris, visible light can't penetrate it. Traditional telescopes see nothing but a murky void, earning it a name that sounds like something from a sci-fi horror story. But hidden behind that impenetrable curtain could be an entire population of dark stars, invisible not just by nature but by cosmic coincidence. Think of the zone of avoidance as the universe's ultimate magician's trick, a place where the ordinary rules of observation break down. The Milky Way's disk is crammed with swirling dust clouds, remnants of dead stars and stellar nurseries so dense they block nearly all optical light from behind them. For centuries, this region was a blank spot on our maps, a no-go zone for astronomers. But where visible light fails, other wavelengths whisper secrets. Infrared and radio waves slice through the dust like X-rays through flesh, revealing structures hidden beneath. And if dark stars are lurking anywhere, this is their perfect hideout. Here's why this matters. The galactic center isn't just crowded, it's a gravitational hotspot where dark matter is thought to pile up in dense, invisible halos. If primordial dark stars formed in the early universe, many would have migrated toward these deep wells of gravity over billions of years, drawn like moths to a flame. But because the zone of avoidance obscures our view, we could be missing a goldmine of these shadowy giants clustered right in our cosmic backyard. The hunt is already underway. Telescopes like the James Webb Space Telescope with its infrared eyes are piercing the dust veil like never before, mapping regions once thought inaccessible. Radio observatories like the upcoming square-kilometer array could detect the faint thermal whispers of dark stars' cold, slow emissions that optical instruments would never catch. Even gravitational microlensing surveys, which track how unseen masses bend light from background stars, are scrutinizing the zone for anomalies, unexplained lensing events that don't match any known object. But the real breakthrough might come from an unexpected source: cosmic ray detectors. If dark stars in the zone of avoidance are actively annihilating dark matter, they could be spewing high-energy particles, protons, neutrinos, even antimatter, that zip through the dust unimpeded. Observatories like the Fermi Gamma Ray Space Telescope have already spotted unexplained gamma-ray excesses near the galactic center, some aligning suspiciously with predicted dark matter densities. Could these be the faint death cries of dark stars echoing through the dust? The implications are staggering. Discovering dark stars in the zone of avoidance wouldn't just fill a blind spot in our galactic map, it would rewrite our understanding of the Milky Way structure. These hidden giants could be the missing mass explaining why the galaxy's rotation curves don't match visible matter alone. They might even hold clues to dark matter's true nature, their behavior revealing how it interacts with itself and ordinary matter under extreme conditions. Yet the zone remains stubbornly elusive. Even with cutting-edge tools, the sheer density of dust and gas means signals are muffled, like hearing a conversation through a padded wall. Some researchers argue we need a dedicated mission, a telescope designed solely to probe this forbidden zone, combining infrared, radio, and gravitational wave detection in one package. Until then, the zone of avoidance keeps its secrets, a cosmic puzzle wrapped in dust, waiting for the right technology to crack it open. So while we gaze at glittering spiral arms and distant galaxies, remember, some of the universe's greatest mysteries might be hiding in plain sight, cloaked by the very fabric of our own galaxy. The zone of avoidance isn't just an obstacle, it's a challenge, a dare from the cosmos to look deeper, to push past the limits of what we think we know. And if dark stars are there, watching from the shadows, they could be the final piece in a puzzle we've been trying to solve since the dawn of astronomy. Einstein once showed us that time isn't rigid, it bends, stretches, and slows down under the grip of gravity. Near a black hole's event horizon, clocks tick at a crawl compared to the rest of the universe. But what if something else, something unseen, could warp time just as dramatically? Dark stars, with their immense gravitational pull, might be invisible time machines, twisting the fabric of space-time so severely that they leave fingerprints on the very light passing by. And one of the most tantalizing clues could be hiding in the death throes of ordinary stars, supernova, whose light curves don't behave the way they should. Take SN 2014J, a supernova that erupted in the nearby galaxy M82. At first glance, it seemed like a typical Type Ia explosion, the kind astronomers use as cosmic yardsticks to measure distances across the universe. But when researchers analyzed its light curve, the way its brightness evolved over time, something was off. The decline in luminosity was subtly distorted, as if something massive and unseen was stretching the light's journey, slowing its arrival in ways that defied standard models. The usual suspects, dust clouds or irregular shockwaves, couldn't fully explain the anomaly, but a dark star lurking between us and the supernova, that would change everything. Here's how it could work. If a dark star's gravitational field lies along our line of sight to a supernova, its space-time warping would act like a funhouse mirror for light. Photons passing close to the dark star would take slightly longer to reach us, some dragged through the stretched time near the object's core, others skimming its edges at less distorted speeds. The result, a staggered light curve where the supernova's brightness doesn't fade smoothly but flickers with minute delays, like an echo bouncing off an invisible wall. For SN 2014J, these delays were small but measurable, a discrepancy of just a few days in a weeks-long event. Yet in the precise world of cosmology, even tiny deviations can hint at colossal secrets. Critics argue that interstellar gas or turbulent magnetic fields could mimic these effects, but the distortions in SN 2014J's light curve had a peculiar symmetry, a pattern that aligns eerily well with simulations of gravitationally lensed light. And while traditional lensing from visible objects like galaxies or black holes is well documented, dark stars would leave a different signature, lensing without a visible lens. No glowing halo, no telltale warp in background starlight, just a silent tug on spacetime, betraying its presence only through the tortured path of light from a dying star. The implications ripple far beyond one odd supernova. If dark stars routinely distort light curves, they could be silently skewing our measurements of cosmic expansion. Type Ia supernovae are critical to calculating the universe's growth rate, but if some of their light has been stealthily delayed by unseen masses, our entire cosmic distance ladder might need recalibration. Even more intriguing, dark star-induced time dilation could explain other lingering anomalies like certain supernovae that appear inexplicably older than their host galaxies, their light curves stretched by eons of gravitational delay before reaching us. The hunt for these hidden time warps is already evolving. Next-generation telescopes like the Vera-C, Rubin Observatory will monitor millions of supernovae, their algorithms trained to flag aberrations in light curves that could point to dark stars. Others might combine gravitational wave data with supernova observations, searching for coincident ripples in spacetime that betray an invisible object's presence. And if we find even one confirmed case, it won't just prove dark stars exist, it'll open a new window into gravity's most extreme playgrounds, where time itself becomes a tool for discovery. For now, SN 2014J remains a cosmic breadcrumb, a hint that the universe's darkest corners might be twisting the very light we rely on to understand it. And if dark stars are out there, warping time in their wake, every supernova we observe could be a test, a chance to catch the invisible red-handed, bending reality to its will. What if dark stars aren't just fueled by dark matter? What if they contain black holes at their hearts? Picture a cosmic Russian nesting doll, a colossal dark star, its invisible bulk shielding something even stranger, a tiny, primordial black hole lurking in its core. This isn't science fiction. It's a radical twist on two of astrophysics' greatest mysteries, one that could rewrite how we think about the birth of black holes and the nature of dark matter itself. The idea hinges on a cosmic paradox. According to conventional physics, stellar mass black holes form when massive stars collapse under their own gravity, a violent death marked by supernova. But there's a problem. The earliest black holes in the universe, some dating back to just a few 100 million years after the Big Bang, are too big. They shouldn't have had time to grow to billions of solar masses so quickly, unless they didn't start as stars at all. Enter primordial black holes, hypothetical relics from the universe's first chaotic moments, forged not by collapsing stars but by extreme density fluctuations in the infant cosmos. These ancient black holes could have been microscopic at birth, smaller than an atom yet dense enough to warp spacetime. Over eons, they'd gorge on gas, dust, and dark matter, ballooning into the monsters we see today. But here's where dark stars crash the party. If a primordial black hole wandered into a cloud of dark matter in the early universe, something extraordinary might happen. Instead of devouring everything around it, the black hole's gravity could trap dark matter particles in a vast, swirling halo, a dark star with a black hole seed. Unlike ordinary stars where fusion fights gravity, this hybrid would be a self-sustaining engine. The black hole's pull compressing dark matter, triggering annihilation, and the resulting energy preventing further collapse. It's the cosmic equivalent of a nuclear reactor with a black hole as its control rod, a perfect equilibrium between destruction and creation. The implications are staggering. For one, it solves the seed problem for supermassive black holes. A primordial black hole/dark star hybrid could grow exponentially faster than traditional models allow, its dark matter fuel feeding the central black hole without the need for conventional accretion. Simulations show these hybrids might reach supermassive sizes in just a few 100 million years. fast enough to explain the giants we see in the early universe. There's another tantalizing clue: gravitational waves. When black holes merge, they send ripples through space-time, but primordial black hole collisions would have a distinct signature: higher frequency waves with bizarre spins, a fingerprint of their exotic birth. LIGO and Virgo have already detected events that don't quite fit standard black hole mergers. Could some of these anomalies be dark star remnants, their primordial cores finally colliding after billions of years in hiding? The most mind-bending possibility: some dark stars might still be out there, their black hole hearts hidden beneath layers of annihilating dark matter. These wouldn't behave like ordinary black holes. Their dark matter halos could deflect infalling gas, making them eerily quiet compared to their ravenous cousins. Telescopes searching for quiet, black holes, objects with strong gravitational pulls but no visible accretion disks, might already have spotted them without realizing it. Critics argue the theory stretches plausibility, but the math holds up. If even a fraction of dark stars harbor primordial black holes, it would reshape our understanding of cosmic history, revealing a universe where dark matter and black holes are inextricably linked. The hunt is on. New gravitational wave detectors like the Einstein telescope could spot the unique chirps of these hybrids merging. Meanwhile, telescopes like James Webb might catch the infrared glow of dark matter annihilation around seemingly empty patches of spacetime. The universe loves a good puzzle, and dark stars with black hole cores might be the missing piece we've overlooked. They're not just scientific curiosities, they're potential keys to unlocking the origins of the cosmos itself. And if we find one, it won't just solve a paradox, it'll force us to rethink everything we know about the dark side of reality. The Boots Void is one of the most unsettling places in the known universe, a colossal sphere of near-nothingness stretching 330 million light-years across, where galaxies are so sparse they feel like lonely waystations in an endless desert. Astronomers call it the Great Nothing, and for good reason. While a typical region of space this size should contain thousands of galaxies, the Boots Void holds only 60 or so, scattered like distant campfires in a cavernous night. At first glance, the void seems like a flaw in the cosmic fabric, a blank spot where the universe forgot to fill in the details. But what if that emptiness is an illusion? What if the Boots Void isn't empty at all, but filled with something we can't see, an unseen population of dark stars silently anchoring this cosmic ghost town? Most explanations for the void's underdensity point to dark energy, the mysterious force accelerating the universe's expansion. In this model, the Boots Void is a natural fluctuation, a bubble stretched to extremes by dark energy's push, thinning out galaxies like smoke in a strong wind. But there's a problem with this tidy story. The void scale is almost too extreme, exceeding what standard cosmology predicts for random cosmic foam. Could something else be at work? Dark stars, with their immense gravitational pull, might offer a tantalizing alternative. Picture a scenario where primordial dark stars formed in this region first, their gravity so dominant it suppressed normal galaxy formation altogether. Instead of stars and gas coalescing into galaxies, dark matter clumped into these invisible giants, their presence warping the surrounding space into a gravitational desert where ordinary matter never stood a chance. The numbers line up eerily well. Simulations of dark star formation suggest they'd naturally arise in regions with high dark matter density early in the universe, exactly the kind of environment that could later stretch into a void. Unlike galaxies, which leave trails of light, dark stars would vanish into the cosmic background, leaving behind only their gravitational footprint. And here's the twist: if they're concentrated in the Boots Void, their combined mass might explain why the void hasn't collapsed under its own gravity. Dark energy alone can't account for the void's stability, but an unseen scaffold of dark stars could be the hidden architecture holding it up. There's even a smoking gun buried in the void's few surviving galaxies. Some of them show unusual velocity patterns, stars moving as if tugged by something massive nearby. Traditional models chalk this up to dark matter halos, but the sheer scale of the anomalies hints at something denser, more localized. Could these galaxies be orbiting dark stars, their motion betraying the presence of invisible anchors lurking in the void? It's a radical idea, but not without precedent. Astronomers have long noted that void galaxies tend to be older and quieter than their cluster counterparts, as if something stalled their evolution. Dark stars could be that something, their gravity-disrupting gas flows and starving these galaxies of the fuel needed to spark new star birth. The hunt for dark stars in the Boots void is like searching for footprints in a snowstorm. Without light to guide us, astronomers must rely on indirect signatures, gravitational lensing distortions in the void's sparse galaxies, or faint whispers of gamma rays where dark matter annihilates. Some researchers are even probing cosmic microwave background data, looking for temperature ripples that could hint at dark star clusters warping spacetime on a vast scale. So far, the evidence is circumstantial, but the mere possibility reshapes how we see cosmic voids. They might not be empty after all, just draped in shadows, hiding giants we're only beginning to imagine. The implications ripple far beyond Boots. If dark stars dominate voids, they could be the missing link in the universe's large-scale structure, the unseen hand shaping the great cosmic web. And if voids aren't truly empty but teeming with dark matter's most bizarre creations, it forces a question we've been avoiding. How much of the universe have we overlooked because we couldn't see it? The Boots void might be the ultimate test, a ghostly arena where dark stars, not dark energy, hold the keys to the deepest cosmic mysteries. One thing's certain, in the great nothing there's more than meets the eye. Deep in the hearts of dark stars, a cosmic alchemy might be unfolding, one that could solve one of the most enduring mysteries in particle physics. Weakly interacting massive particles, or WIMP, have long been the leading candidates for dark matter, hypothetical bits of matter that barely interact with normal atoms yet make up most of the universe's mass. But despite decades of searching, no detector on Earth has ever captured definitive proof of their existence. The problem isn't just that WIMP are elusive, it's that we might be looking in the wrong places. What if the answer isn't hiding in underground labs or particle colliders, but in the cores of dark stars, where extreme conditions could be churning out WIMP at rates unimaginable in any terrestrial experiment? The connection hinges on annihilation. If dark stars are fueled by dark matter particles colliding and converting into energy, the reverse process should also be possible, high-energy interactions producing fresh dark matter. Picture the core of a dark star as a natural particle accelerator, far more powerful than anything humans could build. The crushing gravity, the searing temperatures, the relentless density, these conditions could act like a cosmic WIMP factory, forging new particles in numbers that dwarf even the most optimistic collider predictions. Unlike Earth-bound experiments which struggle to create and detect WIMP in isolation, dark stars would operate on an industrial scale, their cores teeming with collisions that spit out WIMP along with faint, telltale byproducts like neutrinos or gamma rays. This idea isn't just theoretical. Future colliders, like the proposed Future Circular Collider at CERN, are designed to probe energy ranges where WIMP might finally reveal themselves. But here's the catch: these machines can only simulate tiny fractions of the conditions inside a dark star. If WIMP are being mass-produced in these celestial forges, their signatures could already be drifting through space, encoded in cosmic rays or high-energy photons that our telescopes are only now learning to decode. The key might lie in anomalies, unexpected excesses of particles or energy patterns that don't fit known astrophysical sources. One tantalizing clue comes from gamma-ray surveys of dwarf galaxies, where unexplained emissions align eerily with predictions for dark matter annihilation. While skeptics argue these could be pulsars or other mundane objects, the signal's smooth, diffuse nature fits uncomfortably well with WIMP models. If dark stars are lurking in these galaxies, their WIMP production could be the missing piece explaining these observations. Even more intriguingly, certain high-energy neutrinos detected by ice cube particles with no clear origin could be the fallout from WIMP interactions in distant dark star cores, their trajectories tracing back to invisible cosmic reactors. The implications stretch beyond astrophysics. If dark stars are WIMP factories, they're not just hiding dark matter, they're actively shaping its distribution across the universe. Simulations suggest that WIMP produced in these environments might clump differently than traditional cold dark matter, potentially solving small-scale structure problems that have puzzled cosmologists for years. Galaxy formation, cosmic web filaments, even the odd motions of star clusters all could bear the fingerprints of dark stars seeding the cosmos with their exotic products. For now, the hunt remains a race between Earth and the heavens. As CERN next-generation colliders come online, they'll scour energy frontiers for WIMP signatures. Meanwhile, telescopes like the Cherenkov Telescope Array and the upcoming Nancy Grace Roman Space Telescope will scan the skies for gamma rays or gravitational anomalies that betray dark stars' hidden work. If these two paths converge, if lab experiments and cosmic observations point to the same WIMP properties, it won't just confirm dark stars, it'll unveil them as the universe's ultimate particle accelerators, natural wonders where the darkest secrets of matter are forged in the silence of space. The universe has always been the grandest laboratory of all, and if dark stars are the crucibles where WIMP are born, they're not just cosmic curiosities. They're the key to unlocking the true nature of reality itself. The Hubble tension isn't just a disagreement, it's a cosmic crisis. For years, astronomers have measured the universe's expansion rate using two methods, and the numbers won't reconcile. One approach, based on the cosmic microwave background, suggests a slower, steadier expansion. The other, rooted in observations of supernova and nearby galaxies, insists the universe is sprinting faster than expected. The discrepancy isn't a small rounding error. It's a gap of about 7.5 kilometers per second per megaparsec, enough to keep cosmologists awake at night. Most solutions point to exotic physics, tweaks to dark energy, undiscovered particles, or even flaws in our understanding of gravity. But what if the answer isn't in the laws of physics but in the shadows of space itself? What if dark stars are the missing variable in this cosmic equation? Imagine dark stars scattered like invisible breadcrumbs across the cosmos, their collective gravity subtly warping the fabric of space-time. These hidden giants wouldn't just sit idly, they'd act as gravitational anchors, bending light from distant supernova in ways we haven't fully accounted for. When we measure cosmic distances using these supernova as mileposts, dark stars could be skewing the results, making the universe appear to expand faster than it truly is. It's like trying to measure a room with a stretched tape measure. You'd overestimate the distance without realizing something was pulling on the tool itself. The math is compelling. Dark stars, especially if clustered in halos around galaxies or drifting in intergalactic voids, would add an unseen layer of gravitational lensing. This lensing would distort the apparent brightness and redshift of supernova, mimicking the signature of accelerated expansion. Simulations show that even a modest population of dark stars could account for a significant fraction of the Hubble tension, bridging the gap between conflicting measurements without invoking radical new physics. Critics argue that early dark energy, a hypothetical burst of energy in the universe's first few million years, offers a cleaner fix, but this theory has its own headaches. Early dark energy would leave imprints in the cosmic microwave background, subtle wrinkles that haven't been definitively spotted. Worse, it struggles to explain why local measurements of the expansion rate are so persistently high. Dark stars, on the other hand, would leave no such contradictions. Their influence would be localized, affecting nearby supernova more than the ancient light of the CMB, precisely matching the observational split. The real test lies in the data. Upcoming surveys like the Vera-C Rubin Observatory will map the cosmos with unprecedented precision, hunting for the faint gravitational distortions that dark stars would produce. If certain supernovae appear mysteriously brighter or stretched in ways that defy standard lensing models, it could be the smoking gun for these hidden giants. Others are probing the large-scale structure of the universe, looking for voids or filaments where dark stars might congregate, their mass subtly altering the flow of cosmic expansion. This isn't just about resolving a technical disagreement, it's about rewriting the universe's user manual. If dark stars are the key to the Hubble tension, they're not just passive relics, they're active players in cosmic evolution, bending light and warping distances on a galactic scale. Their existence would mean our maps of the cosmos have been missing entire continents of mass, invisible landmarks quietly shaping everything we thought we knew. Until we find them, the tension remains a reminder that sometimes the universe's greatest secrets aren't in the light, but in the dark. What if dark stars aren't just cosmic oddities? What if they're being used? Imagine an advanced civilization millennia ahead of us, searching for the perfect way to communicate across the void without drawing attention. Ordinary stars are too noisy, too bright, their electromagnetic chatter drowning out any intentional signal. But a dark star, invisible to most telescopes, yet massive enough to serve as a gravitational anchor, it could be the ultimate stealth beacon, a hidden node in a galactic communication network, transmitting messages not through light, but through the universe's most elusive particles, neutrinos. Neutrinos are the ideal interstellar messengers. They pass effortlessly through gas, dust, even entire planets, arriving at their destinations unimpeded by the obstacles that scatter or absorb light. A civilization harnessing dark stars could modulate neutrino beams encoding data in their energy levels, timing, or spin, creating a channel so discrete it would be virtually undetectable to anyone not deliberately listening. Unlike radio waves which fade into the cosmic background, these signals would pierce the galaxy with laser-like precision, their dark star amplifiers ensuring the message carries across unfathomable distances. The idea isn't as far-fetched as it sounds. We already know high-energy neutrinos can be artificially produced. Our own particle accelerators create them in controlled bursts. An advanced society might master this on a stellar scale, using the dark star's core as a natural particle collider. Picture a dense, spinning dark star wrapped in magnetic coils, its dark matter annihilation events tuned to emit structured neutrino pulses. To an outside observer, it would look like random noise, but to a recipient with the right decryption key, it could be a library, a warning, or even an invitation. This wouldn't just be communication, it'd be strategic communication. Dark stars clustered in galactic halos or drifting between galaxies could form a relay network, allowing civilizations to share information without broadcasting their presence to potential threats. If humanity ever picks up a repeating neutrino signal from a region with no visible stars, we might not be hearing from a natural phenomenon. We might be intercepting a conversation. The search is already underway. Projects like IceCube and the upcoming Pacific Ocean Neutrino Experiment are refining their ability to trace neutrino origins. Unexplained repeating neutrinos, especially those with unnatural energy distributions or timing patterns, could be the first hint of a dark star transmitter. Even more telling would be a signal that changes, adapting its frequency or sequence in ways that defy cosmic coincidence. Of course, skepticism is healthy. Neutrino detectors are still crude compared to optical telescopes, and false positives abound. But if we're serious about SETI, we can't just look for radio waves or laser pulses. We have to consider that the universe's most advanced engineers might be hiding in plain sight, whispering through the dark. the greatest message in history could be reaching us right now, not from a star but from the void beside it. And if we learn to listen, we might discover we're not alone in the cosmos, just late to the call. Most of the universe's mass is missing, or at least that's what we've been told. For decades, the leading explanation has been dark matter, an invisible substance whose gravity holds galaxies together. But what if we're looking at the problem backward? What if the missing mass isn't matter at all, but a flaw in our understanding of gravity itself? Enter modified Newtonian dynamics, or MOND, a radical theory suggesting gravity behaves differently on cosmic scales. And in this alternative framework, dark stars take on a startling new role, not as dark matter-fueled anomalies, but as natural consequences of the universe's rewritten rulebook. MOND was born from a cosmic discrepancy. In the 1980s, astronomers noticed galaxies rotating so fast that their visible stars and gas should have flown apart unless some unseen mass was anchoring them. The dark matter hypothesis became the default solution, but physicist Mordechai Milgrom proposed a different fix. Maybe Newton's laws break down where gravity is extremely weak. At galactic edges, where acceleration dips below a critical threshold, MOND suggests gravity strengthens just enough to explain those unexpected rotation curves without invoking invisible matter. It's a bold idea, one that rewrites the universe's operating system rather than adding hidden hardware. This is where dark stars get interesting. In standard cosmology, these objects rely on dark matter's annihilation to power their faint glow. But in a MOND universe where gravity's rules are bent, dark stars might not need dark matter at all. Their immense gravity could arise naturally from modified dynamics, compressing ordinary matter into ultra-dense configurations that conventional physics can't explain. Picture a star so massive it should collapse under its own weight, yet held up by MOND-enhanced gravitational pull, a celestial paradox shining faintly at the edge of possibility. The contrast with the standard lambdactym model couldn't be sharper. Where lambdactym needs dark matter halos to explain galactic rotation curves, MOND tweaks gravity's math to fit the data without invisible crutches. For dark stars, this means two entirely different origin stories. In lambdactym, they're dark matter crucibles, their existence proof of an invisible cosmos. In MOND, they're gravity's glitches, objects that only make sense when the laws of physics flex. Both frameworks can explain the same observations: flattened rotation curves, unexpected lensing effects, but their underlying mechanisms diverge wildly. Critics argue MOND struggles with larger-scale phenomena like galaxy cluster dynamics or the cosmic microwave background structure. Yet some simulations show MOND-like gravity could produce dark star-like objects through sheer gravitational amplification, no exotic particles required. The key lies in velocity dispersion, the way stars move within galaxies. MOND predicts specific patterns that, in certain cases, align eerily with observations of low-surface brightness galaxies, the very places where dark stars might lurk undetected. If these galaxies host unusual stellar populations that MOND explains better than lambdactym, it could hint at a hidden kinship between modified gravity and dark star formation. The real test may come from the James Webb Space Telescope. If JWST spots dim, massive objects in galaxies where MOND gravity should dominate objects that shouldn't exist under standard models, it could tilt the scales toward this alternative framework. Likewise, gravitational wave observatories might detect mergers between compact objects with masses that only make sense in a MOND universe. Either outcome would force us to confront an uncomfortable truth: the cosmos might not be missing mass after all. It might just be playing by different rules where dark stars aren't the exception but the inevitable. Whether dark matter or modified gravity wins the day, one thing is clear: dark stars are more than cosmic curiosities. They're stress tests for our deepest theories, lighting the way to a universe far stranger than we imagined. And in that darkness, whether from unseen matter or rewritten laws, lies the next revolution in physics. The KBC void is a cosmic anomaly right in our own backyard, a vast bubble-like region of space stretching over 2 billion light-years across, where galaxies are strangely sparse compared to the rest of the universe. Named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, this void is unusual not just for its size but for its location. It encompasses the Milky Way and our local galactic neighborhood. In a cosmos that's supposed to look roughly the same everywhere, the bedrock assumption known as the cosmological principle, the KBC void stands out like a thumbprint on a blank page. But what if its existence isn't just a statistical fluke? What if it's the result of something unseen, something massive lurking in the emptiness like a swarm of dark stars? The cosmological principle is one of astronomy's foundational ideas. It states that, on large enough scales, the universe should appear uniform, no special places, no dramatic over or under densities. Yet the KBC void defies this expectation. It's 7 times larger than typical voids, and its underdensity is stark, with about 20% fewer galaxies than expected. Some researchers dismiss it as a rare but natural fluctuation, a cosmic lottery ticket that just happened to land around us. Others see it as a crack in the foundation, a hint that something fundamental might be missing from our models. Dark stars could bridge this divide. Imagine these invisible giants congregating in the void's dark matter scaffolding, their collective gravity repelling normal matter over billions of years. As galaxies formed elsewhere, the dark star's gravitational influence might have pushed gas and dust away, stifling star birth and leaving the region eerily empty. This wouldn't just explain the KBC void's underdensity, it could also account for another oddity: the Milky Way's unusually high velocity relative to the cosmic microwave background. If dark stars cluster unevenly, their gravity might be tugging us toward denser regions beyond the void, a cosmic tug-of-war hidden in plain sight. Critics argue that dark matter alone should suffice to explain large-scale structure, no exotic dark stars required. Yet simulations of dark matter distribution struggle to produce voids as extreme as the KBC without fine-tuning. Dark stars, with their concentrated mass and unique gravitational signatures, could tip the scales naturally. Some models even suggest that primordial dark stars born in the early universe would migrate toward underdense regions over time, drawn by the very dynamics that created voids in the first place. The real test may come from gravitational lensing. If dark stars pepper the KBC void, their mass should subtly warp light from background galaxies, creating distortions that don't align with visible matter. Upcoming surveys like the Vera C. Rubin Observatory could map these warps in unprecedented detail, searching for invisible mass where none should be. Even more telling would be the discovery of rogue planets or orphan stars drifting through the void, objects flung from galaxies by the gravitational kicks of unseen dark stars. The implications ripple far beyond the KBC. If dark stars sculpted this void, they might have shaped others, rewriting our understanding of cosmic structure. Worse, if similar voids exist elsewhere, their mere presence could force us to reconsider the cosmological principle itself. Is the universe truly uniform, or are we just beginning to see the shadows of its hidden architects? The KBC void might hold the answer, a silent testament to the power of what we can't see, and a challenge to everything we think we know. Quantum entanglement is one of the strangest phenomena in physics, a ghostly connection where particles instantly influence each other's states, no matter how far apart they are. Einstein famously called it spooky action at a distance, and to this day it defies our classical intuition about how the universe should work. But what if the most extreme cosmic objects, dark stars, could amplify this spookiness to unimaginable scales? What if these invisible giants aren't just lurking in space, but actively weaving a web of entanglement across the cosmos, linking particles billions of light years apart? The idea isn't as far-fetched as it sounds. Experiments like the cosmic bell test have already shown that quantum entanglement holds true over distances of hundreds of kilometers, with particles coordinating their behavior faster than light could travel between them. If nature allows this phenomenon locally, why couldn't it operate on cosmic scales? Dark stars, with their immense gravitational fields and exotic physics, might be the perfect catalysts. Picture the core of a dark star as a quantum pressure cooker, where the insane density and energy conditions force particles into entangled states that somehow persist even as they escape into the wider universe. Unlike ordinary stars whose radiation and magnetic fields would disrupt delicate quantum connections, dark stars' cold, stable environments could preserve entanglement like cosmic refrigerators, keeping particles in sync across unfathomable distances. Here's where it gets wild. If dark stars act as entanglement hubs, they could be facilitating a form of quantum communication we've never imagined, not with lasers or radio waves, but with particles whose fates are mysteriously intertwined. Imagine two photons emitted from opposite sides of a dark star, their properties linked through entanglement. Even if one ends up near a galaxy in the Boots void and the other in the heart of the Milky Way, measuring one would instantly determine the state of the other. For an advanced civilization, this could be the ultimate encryption system, sending unhackable messages encoded in entangled particles, with dark stars serving as the universe's quantum routers. The implications for physics are staggering. Quantum entanglement is famously fragile, collapsing at the slightest interaction with the environment. Yet if dark stars can somehow shield or stabilize entangled states, they might reveal new laws of quantum gravity, rules that govern how entanglement behaves in extreme gravitational fields. Some theorists speculate that dark stars could even be entanglement factories, producing pairs of particles whose quantum links are somehow reinforced by dark matter interactions. If true, studying these objects could finally bridge the gap between quantum mechanics and general relativity, two frameworks that have resisted unification for a century. The wildest possibility, dark stars might already be entangling the universe on scales we can't yet detect. The cosmic microwave background, the afterglow of the Big Bang, shows faint anomalies, patterns that don't quite fit standard models. Could these be the fingerprints of primordial dark stars imprinting quantum correlations onto the early universe? Future telescopes, like the James Webb Space Telescope or next-generation SETI observatories, might spot these subtle signatures, uncovering a hidden quantum architecture woven into the fabric of spacetime itself. Of course, skepticism is healthy. No experiment has ever confirmed quantum entanglement over interstellar distances, let alone cosmic ones. But if dark stars are as strange as theory suggests, they could rewrite the rules entirely, turning the universe into a vast, interconnected quantum network. Whether they're cosmic telegraphs or just another mystery in the dark, one thing is certain: entanglement isn't just a lab curiosity anymore. It might be the hidden language of the cosmos, spoken in whispers between particles separated by lifetimes of space, and dark stars could be the ones holding the conversation together. From invisible primordial giants lurking in the voids between galaxies to quantum, entangled beacons whispering across spacetime, the 25 dark star hypotheses we've explored aren't just science fiction, they're a radical reimagining of reality itself. Each theory peels back another layer of the cosmos, revealing how these shadowy titans could solve mysteries that have haunted physicists for decades. Imagine confirming that quark-novae dark stars rewrite the life cycle of stellar remnants, or discovering that rogue dark stars drifting between galaxies hold the missing mass of the universe. Picture proving that the Boots void isn't empty at all, but teeming with dark matter anchors bending the fabric of space. Every one of these ideas isn't just a footnote in astrophysics, it's a potential revolution. The implications ripple far beyond astronomy. If dark stars exist, they could be the key to unlocking dark matter's true nature, bridging gaps in quantum gravity, or even explaining anomalies in the cosmic microwave background. They might rewrite the story of how galaxies form, why the universe's expansion rate defies expectations, or how black holes grew so large so quickly after the Big Bang. Some could serve as cosmic particle accelerators, churning out WIMP or actions in quantities no lab on Earth could match. Others might function as invisible time machines, distorting supernova light curves and forcing us to recalibrate the age of the cosmos. And let's not forget the most mind-bending possibility that advanced civilizations could be using dark stars as neutrino transmitters, turning them into interstellar communication hubs hiding in plain sight. But here's the catch: we're standing on the edge of discovery. Next-generation telescopes like the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, and the Einstein Gravitational Wave Detector are poised to turn these theories into facts. The Rubin Observatory alone will scan the entire visible sky every few nights, hunting for the faint gravitational lensing distortions or anomalous microlensing events that could betray a dark star's presence. The James Webb Space Telescope's infrared eyes might catch the cold glow of axion-photon conversion halos, while the square-kilometer array could pick up the radio whispers of quark-novae remnants. This isn't just about adding new objects to the cosmic catalog, it's about rewriting the rules of existence. So which theory resonates with you? Are you drawn to the eerie elegance of Planck stars, quantum relics from the universe's first moments? Or do the Fermi Bubbles' dark matter annihilation fires seem like the most compelling clue? Maybe you're captivated by the possibility that G2, that enigmatic object near Sagittarius, a star, is a dark star in disguise. Drop your favorite idea in the comments. I'd love to hear which cosmic mystery keeps you up at night. And if you're as fascinated by these shadows in the void as I am, consider supporting the astronomical missions that could bring them into the light. Because the universe's greatest secrets aren't always hidden in the stars. Sometimes they're hiding just out of sight, waiting for us to look deeper. The next chapter of astrophysics isn't written yet, and with your curiosity fueling the search, who knows what we'll uncover next?